In the previous video, we looked at three examples of systems of linear equations where one of them gave us a unique solution and one had no solution and the other had an infinite number of solutions. So we are going to formalize this in the next theorem where we show that these are the only options for a system, for any system of linear equations. So we are going to look at theorem 2.3.13 in the textbook, and it says, for any system of linear equations, exactly one of the following statements is true. Number one, the system has no solutions. Number two, the system has exactly one solution. And number three, the system has an infinite number of solutions. Right, so if we write our system in matrix form, we will have AX equals to B, where A is the coefficient matrix and B the column vector containing the right-hand terms of the equations making up the system. So assume that 1 and 2 are false. So in other words, we are saying it has solutions. That's what it means for 1 to be false. It has solutions and it has more than one solution. So in other words, we are assuming that it has more than one solution. So we want to show that if it has more than one solution, then it has to have an infinite number of solutions. Okay, so if it has more than one solution, it means it has at least two. So what it means is then there exist vectors x1 and x2 which are not equal, that are solutions to the system, and we are going to call that 2.6. These two solutions, or rather these two equations, right? So suppose we have got we define a function x of t, which is defined as x1 plus t times x2 minus x1, where t is a real number, right? So we want to show that for any t that we pick, it will be a solution and then make it an infinite number of solutions, right? So it follows from theorem 2.2.15 and theorem 2.2.16, 1 and 4, that we can, so if we take ax of t, we can distribute, so we can say if we substitute x of t with that, we have a times that, and then we can then distribute the a, and we can take out the t, and then we are left with a system like that. So therefore 2.6, so in other words, if we look at 2.6, we are talking of this, implies that ax of t will be equal to, if we look at ax of t, it's equal to this. So this from 2.6, this is b, and then that is b from 2.6, and then that also is b. So in other words, we've got b plus tb minus tb, which is equal to b. So in other words, x of t is a solution of the equation ax is equal to b for every real number t. But we want to also now check that if we take two different t's, do we also have different x of t's? Because if we do, then that means for any t that we pick, it's a different solution from another different t that we would have picked, right? So if we pick two t's, t0 and t1, that are different, then x of t1 minus x of t0 will become the product of that, And if you look at the product, you can see that x2 minus x1, we know they are different, so this is not equal to 0. And so if we pick them to be different as we have picked here, it means that this product is going to be different, right? So because this product is different, this product is going to be uh, different from 0, so it's not equal to 0. So because it's not equal to 0, what it means is uh, x of t1 minus x of t naught is also not equal to 0, meaning that x of t1 is not equal to x of t naught, right? So that's what it means. And because that's what happens if we pick any t, it's going to be different from another t that we pick. So, and because t ranges uh, um, from minus infinity to infinity, it means that this system has infinitely many solutions, so that 3 is true. So what it means, so what we have proved is we assume that 1 and 2 are not true, so they are false, and we show that if this is the case, then the third one has to be true, right? So what does that mean? That means that uh, at least one of the statements is always true. That's what we have proved, because we assume that two are not true, and we show that if those are not true, then that means the third one is not true. And then the other issue, the other point we have to make is, so we've shown that at least one is true, but there might be a situation where uh, maybe they are true at the same time, right? So they are true simultaneously. But if we look at at the statements, we can see that not it any system will have, for any system, at most one of these will be true. There are no two statements that can be true simultaneously for a certain system, because if it has no solutions, it can then have exactly one solution, or if it has exactly one solution, it can have infinitely many solutions and no solutions at the same time. So it means that at most one of the statements has to be true, and we have shown that at least one is true, so therefore exactly one of the statements is true, right? So we now have this theorem, and so we know what to expect whenever we are given any system. We know what to expect. We know all the options, right? Now let's look at definition 2.3.14. It says a system of linear equations is consistent if it has one or more solutions. If it has no solution, the system is called inconsistent, right? So if we have one or more solutions, so one or an infinite number of solutions, we call it consistent. And if it has no solution, then it's called inconsistent, right? So we are going to look at how we can determine if a system is consistent or inconsistent, right? So and this is theorem 2.3.15, and it says let A B represent a system of linear equations where the m by n matrix is in echelon form, right? Then the following statements are true. The system is inconsistent if and only if the coefficient matrix A has a row with all entries equal to 0. So it has a row of zeros, and the corresponding entry of the column B, so the one that will be on the right, is not equal to 0. So in other words, what it's simply saying here is you will have an equation which says 0 plus 0 plus 0 plus 0 is equal to something that is a not 0. So obviously we know that is impossible. So that will tell us that definitely that system has no solution, right? And remember what we said: if it has no solution, we call it inconsistent, right? And then if the system is consistent, it has a unique solution if and only if m is greater than n and akk is not equal to 0. So the and this is for all k uh, from 1 up to n. So what it's simply saying is for us to have a unique solution, the number of rows has to be greater than the number of columns, and all the elements in the diagonal entries cannot be equal to 0, right? So we'll see with some examples how that works. And then if the system is consistent, it has an if the system is consistent, it has an infinitely many solutions if and only if the number of rows is less than the number of columns, or uh, some diagonal entries are zeros, right? So that's what it's saying, right? Now let's look at an example. This is 2.3.16. So it says consider the system of linear equations with corresponding augmented matrix 20. Sorry. Consider the system of linear equations with corresponding augmented matrix, and we are given the augmented matrix. So we want to determine. So where k is a real number, we determine the values of k for which the system has a unique solution, no solution, and infinitely many solutions. Right. So let the coefficient matrix be A. Right. So this part is what we are calling A. Right. Since A is square, it follows from theorem 2.3.15 part 2 that the system has a unique solution if and only if all the entries of the main diagonal are non-zeros, right? So here I think this is supposed to be m is greater or equal to n. I'll verify in the textbook, but I think yes, I think it's m greater or equal to n. I think m because if it's a square matrix, it should work. So this should be m greater or equal to n. Anyway, okay. So and so for it to have a unique solution, we know that the diagonal entries have to be non-zeros. So so the system has a unique solution if and only if, for that to happen, this is not supposed to be 0 and that is not supposed to be 0, right? So in translation, so k can't be equal to 0 for it to have a unique solution. K is not equal to 0 for that part to not be equal to 0, and k squared minus k minus 2 cannot be equal to 0. And but that just means that if k squared minus k minus 2 is not equal to 0, it means k is not equal to 2 or k is not equal to minus 1. So for these three cases, that's when we get a unique solution. Now we want to check for the other two cases. Right. So when k is equal to 0, because these are the only other options that we are left with. So whenever k is not this, we know we have a unique solution. So now we want to check on a case by case to see when k is equal to 0, what happens? When k is equal to 2, what happens? When k is equal to minus 1, what happens? So when k is equal to 0, that means that part is 0, and then that the last part here, it will be 0 minus 0 minus 2, and then that side minus 2. So we'll have a system like this. But this note that this is not in echelon form, so we have to reduce it to echelon form with one operation, and the operation is we want to make this a 0, so we say minus 2 plus 2 times 1 for us to get the row operation. In other words, R3 plus 2 times R2. So minus 2 plus 2, that's 0, minus 2 plus 4, that's a 2, right? Minus 2 plus 4, okay, yes, that's a 2, sorry. So yes, that's a 2. So therefore we have got that. Now from the last row, if we look at the last row, we can see that from theorem 2.3.15 that we have got zeros on the left hand side, and then on the right hand side we have a non-zero, which means that the system has no solutions because this system is inconsistent, right? Let's get on to k is equal to minus 1. So when k is equal to minus 1, if you plug in minus 1 there, you've got a minus 1 there, and then minus 1 squared plus 1 minus 2, and you get a 0 there, and then minus, so this was k minus 2, so minus 1 minus 2, you get minus 3. And then again, from looking at that and using the theorem that we just looked at, we can see that the system has no solutions again because the system is inconsistent. Now let's look at when k is equal to 2. So if k is equal to 2, then the augmented matrix looks like that, and we can see that m, so the number of rows, is less than the number of columns, and so therefore that means that the system has infinitely many solutions. So just by looking at a system in its echelon form, we can determine the nature of solutions that we are going to get. So that is all for systems of linear equations. The part on echelon form. We will continue with matrices in the next section. Thank you.